The next speaker is Michael Sentef, and talking about Magnon Topology. And
thanks, Arun, and thanks for putting together this very nice focus workshop. Feels like a March meeting session without or with cheaper and better coffee. Basically, I'm presenting work that was done by this postdoc Emil Brustrom and the other collaborators shown here. And I'm talking about optical probing of Magnon topology in generally 2D quantum magnets, and I will show the model in a second. And basically the question that I'm addressing, and correct me if I'm wrong, but nobody has specifically talked about the topology quite yet, or at least only touched on it. So the question that I'm addressing is, how can we probe the Magnon band topology or Berry curvature? So that is generally an issue, of course, because as you know, for electrons, you have the transport measurements, but magnons are bosons. So generally, they first of all, you cannot just fill a band easily. You'd have to raise temperature or something, that play some game like that, but there are other issues. So usually these Magnon bands are not only thermally populated, they condense near k equal to 0, what is more. But as you've already seen in the talks earlier, that the Berry curvature in these materials usually is localized near k and k prime. So these are basically two issues. So we need to excite the system somehow. And one photon generally is not enough if you want to reach the Dirac points in these materials. All right, so what we suggest is to use circular dichroism in a 2 Magnon Raman scattering experiment, and that can access Magnon topology. Now, we just heard 2 beautiful talks about Raman scattering, mostly about phonons. What is circular dichroism, and what we mean by circular dichroism in a Raman experiment? We mean that we consider the Raman cross-section difference between incident light with left and right-handed circular polarization, okay? And the motivation for this entire project, and the idea actually came from a different project that we did earlier, where we looked at the dichroism in photoemission spectroscopy that can tell you something basically about the orbital magnetization of the electrons in the material. And that is a measure of the Berry curvature difference, more or less, between, let's say, a valence band and a conduction band, okay? So this paper we published earlier, notice that this is a hemispherical analyzer for ARPIS. This is not Raman, but the idea is very, very similar. So what is the model that we're looking at? It's generally a Canted antiferromagnet. I'm writing the Hamiltonian down here. So it's just a 2D, just one layer. We have some exchange interactions. We have a Dzerzhinsky-Muria term, and we add a magnetic field for good measure here. No Kitaev interactions here, but one could also add those. And basically, what you wind up getting is, if depending on the signs of these interactions here, for example, we consider an in-plane antiferromagnetic interaction. So the system will be antiferromagnetically ordered without the magnetic field, and then the magnetic field cans the spin out of the plane. But the model is not so important. The mechanism is quite general that I'm going to discuss. And basically, this model has a phase diagram. So I should mention that this model was mostly geared towards MNPS3 and similar materials, but you could also twist it or tweak it towards the trihalides, single layer, also multi-layer in principle. So the phase diagram of this particular model here is looks like so. So as a function of the Dzerzhinsky-Muria and the magnetic field, you get different topological phases with different Chern numbers. The Chern number here always refers to the Chern number in this acoustic branch, and you have the opposite Chern number in the upper branch. Okay, and the Berry curvature distribution was already shown earlier, I think. Generically looks like this. Yeah, so it's mostly localized near these Dirac points. And again, the Berry curvature is, the structure is more or less the same, but it has the opposite sign for the lower and upper bands of the magnets. Okay, so now, as I already said, there are basically two limits of this model. One is the ferromagnetic limit, where you get a non-trivial topology, but it's difficult to excite because the dominant excitation process for Magnon Raman scattering is a single Magnon Raman scattering where you have direct vertical transitions. Whereas in the antiferromagnet, you have a trivial topology, but they're easier to excite because you can have as a dominant process this two Magnon pair creation process. Okay. So now, when you look at how do the magnons actually couple to light, we did some calculations, and here is a snapshot of the band structure between the k and k prime points going through the M point. And what you see is on the right-hand side is the probability for these different Magnon pair creation processes in the Raman process. The probabilities for an incident photon of right-handed polarization that scatters into a left-handed one, and vice versa. So red is R to L, and sorry, the upper panel is R to L, the lower panel is L to R. Red and blue encode the different bands of the magnons. And what you see is that if you do the R to L process, predominantly you excite Magnon pairs in the lower band, whereas the opposite, it's in the opposite case, L to R, it's vice versa. You predominantly excite magnons in the upper band. Okay. And the reason for that is actually basically that you can think of these topological magnons as having some kind of orbital angular momentum, or orbital magnetization, I should say. And basically this gets imprinted onto the photons. So if you come in with a right-handed photon and create a pair of magnons, the photon polarization mainly switches from right to left, and this process is performed, so to speak, by the Berry curvature and the quantum geometry of the magnons. So this suggests a relation between light matter coupling and quantum geometry. And we worked this out in a bit more detail. So this you all know, quantum geometry, introduced by Berry famously. And basically what we do here is we take the initial Hamiltonian that I showed earlier, do a spin wave expansion, and then basically couple it to light. You can couple it in different ways. I'm not going to go into the details here, but more or less this amounts to replacing k by k minus a. So this looks like minimal coupling and should be familiar to you. And now you can expand the Hamiltonian systematically in orders of the external field of this vector potential, which belongs to the photons in the process. And you find very analogously to the electronic case, different derivatives of the Hamiltonian with respect to the momentum, as you know from the electronic case. Yeah. So importantly, these light matter couplings are now given by derivatives of the Bogoliubov matrices that appear when you do the spin wave expansion and the transformation to diagonalize the spin wave Hamiltonian. And again, there's a related story for charge instead of spin that I just want to briefly point out. Yeah, so this was already done for charge instead of spin. And the key message here is that there is a direct relation between the quantum geometry, which is encoded in these derivatives, and the light matter coupling that you get as the functional derivatives of the Hamiltonian with respect to the vector potential. Okay. So now what does this have to do with the Raman circular dichroism? Well, now we define a Raman circular dichroism as I said before. So this is the total Raman cross section for incident light with right or left-handed polarization. You take the difference, and this is the chi, which is the RCD. Okay, and what Emil now produced is the following. So I showed you earlier this topological phase diagram where we tune the Dzerzhinsky-Moriya and the magnetic field. And voila, if you look at the Raman circular dichroism, you see that it changes sign exactly where you change from the turn +1 to the turn -1, for example, along the y direction here. So along as you tune the magnetic field, and similarly for the Dzerzhinsky-Moriya tuning. Yeah. So of course here we assume that we have a tuning knob. In reality, of course, the Dzerzhinsky-Moriya is whatever it is, but the magnetic field can be tuned, as you saw earlier. So this is the integrated frequency integrated signal. This is already great, but actually we can do better. as you know, and we can do the frequency resolved calculations as well. So here I'm showing some evolution of the Magnon band structures as a function of the magnetic field here, I think, as a tuning parameter. This is the corresponding density of states that I'm showing here on the left. And on the right, I'm plotting the frequency resolved Raman circular dichroism. And you notice that all of the intensity actually comes from this region where the gap is between the upper and lower bands. Yeah. So this already very suggestive that there might be more interesting information in the signal. Importantly, the frequency resolved RCD probes the topological gap. I'm showing this here on the next slide. So here I'm basically just plotting the two things. So I'm plotting the topological gap, and I'm plotting the peak-to-peak distance in the frequency resolved RCD, and they line up perfectly. And what's more, actually, we can explain the RCD signal as more or less a product of two things, namely the two Magnon density of states, which is known to be the relevant quantity, so to speak, for the Raman intensity in the first place, and the Berry curvature. Yeah. So what I'm showing here is basically the dashed line is this two Magnon DOS. The other two curves are the frequency resolved RCD for one example of parameters, and together with it the density of states multiplied by the Berry curvature. So this really tells us that there's a rich information in this signal. What you should remember from the talk, if you remember nothing else, is that the RCD is basically this two Magnon DOS times the Berry curvature. If you prefer a pictorial representation, notice that this is not RCD but ARPAS, but okay, never mind, I didn't have a better figure. But basically RCD is DOS times Berry. Emil did all the hard work, and I thank you for your kind attention.
Thanks a lot, Michael, for a great talk. And we're on time, so we have time for a couple of quick questions. I see Rolando has one in the chat. He can just unmute and ask. Peter has another question after that.
Yes.
Go ahead.
Yeah.
Oh, Rolando, you seem to be muted, or is it something from my end?
Am I muted still?
Yeah, it's fine. Yeah.
Okay. So I was asking, does your model require an out-of-plane component of the spin, or
does
meaning
my
a
model
ferromagnetic component?
No, it doesn't. Not at all. That just happens to come about by the magnetic field. So we're just looking for a simple model where we could tune between these different phases. Okay. But no, you can have a fully in-plane spin, doesn't matter. Yeah. So also the antiferromagnet, the pure antiferromagnet in this case actually is, now I need to remember if I'm not that I'm not saying something stupid. Well, the Canted one has an out-of-plane component. The AF, I guess, also does. Right. I don't think so. So I think I stick to my initial answer, but I'd need to check more carefully. I don't think so.
So Peter.
Michael, I'm wondering. So this is interesting. You're sensitive to the sign of the Chern number, but maybe there's some rules that you could take advantage of to get not just the sign, but its magnitude, and then you kind of divide these things by universal numbers, and you can get 1 or -1. So you're actually sensitive to the Chern number itself. People in Raman don't usually worry about magnitudes, but I think that this is the magnitudes of signals. But this is probably, that's just because there's there's no good reason to do it. People like Rolando and Leon could try to maybe get magnitudes if there was a. I don't know if there's an intrinsic difficulty or not, but it seems like that there should be some, something in the spirit of the F-sum rule that allows you to get not just the sign, but also actually the quantized number.
The quantized number, yeah, that might be, wow. Maybe, but I'd need to think about how you would. I mean, from the Raman, wouldn't you need some kind of reference measurement
Yeah,
Because
you
you
would
just
probably need to
like-
do that, but that's something for the experimentalists to work hard about.
Right. I should also mention that I was sweeping something under the rug in my talk, and I only realized that recently. And now I have a great. So I'm asking a question to the audience, unless there are other questions to my talk.
I think there's one quick question, maybe. So maybe, I don't know, Michael. So maybe we can come back to this in the panel discussion. There's just one
that's fine.
question here from Darshan Joshi. So can you distinguish the case from where the total churn number is 0, but the Berry curvatures are, have opposite signs, maybe at the two Dirac crossings? Maybe
that might be much harder, right? Because the problem is that we don't have K resolution, or the problem is that the experiment doesn't have momentum. In principle, in the theory, we could resolve momentum as well, but I'm not, off the top of my head, I don't have a good idea how you would distinguish. What you're saying is that if you have a K and K prime, you have opposite Berry curvature in the same band.
For instance, I think that's what Darshan has in mind. Yeah.
Yeah, that's an awesome question. That's an awesome question. Let me think about it.
We can come back. There's another question about like cavity type setups, but maybe we can come back to this during
cavity. I think is an entirely different story. Yeah.
So let's do one thing. So this is the last talk in the second session. So let's thank all the speakers in this session. So Inhi, Rolando, Luan, and Michael. Thanks everyone.